Hello everyone. In this video we will continue to examine topic 5.2, the heating effect of electric currents. Alright, in the last video we defined resistance and we observed the relationship between potential difference and current. And in particular, resistance is defined as the relationship, the ratio between potential difference and current. And we briefly mentioned this, but there's an important, really essential sort of underlying idea here, which is that although resistance is defined this way, it depends on the properties of the circuit element itself. So it depends on the physical microscopic properties of the circuit element. And this is exactly kind of like mass. So mass can be defined as the ratio between the net force and the acceleration on an object, but it depends on the object, not the forces on it, nor the resultant acceleration. So that then begs the question, okay, what are the properties of the circuit element on which the resistance depends? You can test this experimentally, but fundamentally, the phenomenon of resistance, this idea that it's sort of something is pushing against the flow, or sort of slowing down the flow of charge through an object, is due to how much the internal atoms or molecules of the material are slowing down or obstructing the moving charges. If there's more stuff in the way, or it's harder for charge to move in the object, then you get a higher resistance, basically by definition. This is an example of a resistor with a current through it and a potential difference across it. And if we zoom in a little bit, what's actually happening, recall, is that these fixed positive ions here in green are sort of fixed in place. We're considering a metal resistor right at this moment, but fixed in place in that metal resistor, and the electrons themselves are what are moving. Notice that if the potential difference and the conventional current, so the potential difference is positive and the conventional current is to the right, then what that means is that the electronic current, or the electrons, are actually moving to the left here. And it's the collisions of these electrons with the positive ionic lattice made up of these positive ions inside the metal that forms the resistance. When those electrons collide more with those protons, your resistor heats up. So internal energy of that resistor grows, and that is effectively energy transfer from the battery or the source of the EMF to the resistor itself. And physically, that's what's going on. So what properties of a resistor does this then depend on? Well, experimentally, you can actually derive some pretty straightforward and relatively easy to understand relationships. The first is that of length. So if your resisting element, so if this thing right here in your circuit is longer, then the resistance is higher. There's simply more positive charges for these electrons to run into on their way from point A to point B. So the higher L is, the higher the resistance. The second thing it depends on, and this is less obvious but also true, is the cross-sectional area. So if this is sort of a cylindrical resistor here, the cross-sectional area is the area of the face. And it basically corresponds to the idea that the wider the pathway is, the sort of more expansive that pathway is, the easier it is for the electrons to move through it. So even for the same object of the same length, if you make it thicker, make the cable thicker, for example, you have much lower resistance. And finally, sort of the obvious candidate is the material. It matters a great, great deal what the material is made of. Is it a very highly conducting metal? Well, it'll have a very low resistance. Is it a very heavily insulating plastic? Well, then it will have a very, very, very high resistance. And this material, okay, so the nature of the material, is characterized quantitatively by what is known as the resistivity. Okay? It's a formal term given the symbol rho. And The general idea is that you can empirically calculate the resistance of any single piece of material, so rather than a combination, but a single piece of material, by taking the resistivity, which is a function of the material, and also its temperature. So as temperature changes, different materials change in resistivity. We'll talk more about that later. Times its length divided by the cross-sectional area. So if the cross-sectional area goes up, the resistance goes down. If the length goes up, the resistance goes up. This is a relationship you should be comfortable with and familiar with moving forward.